Hi, I'm Zor. Welcome to User Education. I would like to talk about something I would say interesting and creative in trigonometry, which is related to trigonometric series. Now, series, as we know, is basically a sum of certain members. Now, trigonometric series is obviously when these members represent certain trigonometric function of some arguments. So, just as an example again, this would be an example of trigonometric series. Well, what's interesting about these is that there is actually an interesting practical usage of these things. You see, sine and cosine functions, they represent oscillations. So whenever certain oscillations are added together, for instance, you have some source of radio frequencies and another source of radio frequencies, they are actually somehow combined. Now, let's just forget about all these practical issues and let's concentrate on mathematics. What I would like to present today is one particular problem related to trigonometric series. And what's interesting about this problem is it's on the border between trigonometry and algebra and geometry, if you wish. And it's using this connection between trigonometric functions and complex numbers. So, let me just present the problem, and you'll judge yourself whether I'm right actually to be quite excited about what kind of a problem this actually is. Okay, so here is the problem. Let's say you have to summarize sine of phi plus some delta plus sine of phi plus 2 delta plus etc. plus sine of phi plus, what's the last one? N minus 1 delta. So I have n members from no delta to n minus 1 delta added to original angle phi. Now, absolutely similar can be a cosine. Okay, so it's two problems, but actually it's one problem. I'll combine them together. Now, there are different ways to solve this problem. How to find this particular sum, let's call it S sine or S cosine. I will offer the way, the methodology, which I consider very interesting, very creative, and somewhat, well, I'm not afraid of this word beautiful in this particular case. That's one of the things in mathematics which definitely can be beautiful, but to reach them you have to really accumulate a certain amount of knowledge to be able to use it. So how can I solve this particular problem? How can I express this sum in a more concise way? Here is the way which I suggest. And again, this is not the only way. Obviously there are others, but this I particularly like. Let's just recall that any complex number let's say we have this complex number. It can be expressed geometrically as a point with coordinates x and y, right? Now, you remember that this distance from the origin is called the modulus, right? Now, let's consider only complex numbers on the unit circle. So those complex numbers with modulus equal to 1. Now, modulus is obviously x squared plus y squared in this case. So x squared plus y squared equals to 1. That's the numbers which we are considering. Now, every point on the unit circle can be represented by its angle phi, right, with an x-axis. And at the same time, there is a definition that abscissa and ordinate of this angle phi are abscissa is cosine phi and ordinate is sine of phi. That's by definition of cosine and sine. So if this is an angle phi, this point belongs to a unit circle, then this particular piece is equal to cosine of this angle, and this particular piece is equal to sine. Which means that x is equal to cosine and y is equal to sine. So I can always put this. So any complex number with a modulus 1, which lies basically on the unit circle around the origin, can be expressed in this way, where phi is an angle, which radius to this point makes with the positive direction of the x-axis. All right, so I just reminded you this. I obviously talked about this in the corresponding lecture. Okay, that's one thing. Now, another thing is, let's say that I have two different complex numbers. This is one, and this is another. Both of them are on the unit circle. Both of them have modulus 1. Now, obviously, their product also has modulus 1, because the modulus of the product of complex numbers is the product of modulus, so it's 1. Now, where exactly this particular product be on this unit circle? So if this is angle phi 1, this is angle, let's say, phi 2, where exactly is the product of these two numbers be? Well, let's just multiply them, right? I'm basically repeating something which I have already presented to you in the corresponding lecture about the connection between complex numbers and trigonometry. But anyway, let's just derive this again. I mean, I don't mind to derive it. So multiply these two things. So what will be the real part? This will be cosine by cosine, and also sine by sine, because I squared would be equal to minus 1. So the real part of the product would be cosine phi 1 times cosine phi 2 minus sine phi 1 sine phi 2. What will be the complex, the imaginary part, coefficient with imaginary part? I times sine phi 1, but cosine phi 2, right? Sine phi 1 cosine phi 2 plus sine phi 2 cosine phi 1. Now, we immediately recognize that this is a formula for a cosine of a sum of two angles, and this is the formula for a sine of sum of two angles. So basically what you can say is that z1 times z2 is equal to cosine of their sum plus I sum, sine of their sum. So that's all as a kind of introduction to the methodology which I would like to present you. Now this is all basically the old knowledge which we all know about. Whenever you are multiplying two complex numbers with the modulus 1, their product would be also the complex number of modulus 1, and the angle would be equal to the sum of angles. In some way, by the way, it resembles logarithms, if you remember. Logarithm of the product is equal to sum of logarithms. Here is actually the same thing. Angle of the product is equal to sum of angles. In some way it's similar, if you wish. All right, so knowing this, I would like to use this particular feature for the following purpose. Let's u, one complex number, be cosine phi plus I sine phi. This is one complex number which I am talking about. Another complex number v is cosine of delta plus I sine of delta. Two complex numbers. Now, using these two complex numbers, what will be u times v? Well, if I multiply one complex number with an angle phi by another with an angle delta, I will have a complex number with angle equal to sum of these angles, right? What if I will multiply again by v? This by v. Again, my angles will be added together. Obviously, if I put the third power of 3, it would be 3, and if I will have power of n minus 1, I will have cosine phi plus n minus 1 delta plus I sine phi plus n minus 1 delta. Looks familiar, right? The real part of these numbers is equal to my my sum of cosines, and the imaginary part equals to the sum of sines. So let's just sum them up together. So sum u and all these guys. So what I will have? Cosine of 5 plus delta, 5 plus 2 delta, etc. 5 plus n minus 1 delta. So this would be s cosine plus I sine. Sorry. S sine. Well, that's what I will have on the right side. What will I have on the left side? What is u plus uv plus uv squared, etc., plus u to the v to the power of n minus 1? Well, obviously it's a geometric progression, and we know how to sum geometric progression, right? Well, for those who don't remember the formula, and that actually includes myself, let's derive it. So if you have s equals to u plus uv plus uv squared plus etc. plus uv to the power of n minus 1, it's capital N. Then I multiply this sum by v, so v times s equals to u times v would be uv, uv times v would be uv squared, and the last one would be, whenever I multiply this by v, I will have uvn, uv to the power of n. Now, if I will subtract them, these members will all be reduced because I'm subtracting. The only thing which will be remaining is this and this, from which I can derive that s is equal to u v to the power of n minus 1 divided by, if I subtract this, would be ds times minus s, it's v minus 1s, right? So I divided by v minus 1. So this is my formula. And that would be on the left. I don't need this anymore. All I need is this formula where u is a cosine phi plus I sine and v is cosine delta, right? So my result would be cosine phi plus I sine phi. This is u. Cosine phi delta, that's v, plus I sine delta to the power of n minus 1 divided by cosine delta plus I sine delta minus 1. That's how we use this formula. And this is, as I was just saying, it's s cosine plus I s sine. So, almost done, except, I mean, I can probably multiply something without any problems, except I have to raise to the power of n, right? But that's exactly the same as we did before, because what is this? Well, we are multiplying one complex number with an angle delta by itself n times, right? So whenever we multiply it once, if I do cosine delta plus I sine delta, if I will multiply it by itself once, what will I have? Well, whenever I multiply two different complex numbers, which both have modulus 1 and angles such and such, angles are added together, right? So cosine 2 delta plus I sine 2 delta. Now, if I will multiply it again by the same number, I will have 3, right? I will multiply this by another cosine plus I sine. It would be 3. So if I multiply it n times, obviously I will have n. That's what cosine delta plus I sine delta to the power of n is. So that's how I can put it here. And my formula would be n delta, n delta. Now, is that the end of it? Well, not quite, because I have derived a complex number, and this is a representation. If I will be able to represent this, which is a complex number, in the form like a plus bi, this, then I can say that a is s cosine and b is s sine, right? Now, this is a problem, but it's a technical problem. There is nothing creative about this. All I have to do is really do the multiplication and division, and I know how to do multiplication and division in complex numbers. Just as an example, I mean, if you really want to know what, for instance, you have to do if you have to multiply this by this. Well, you all know that the real part would be AC, and BI times DI would be BDI squared, which is minus BD, so that would be the new real part. And imaginary coefficient would be BC plus AD. So that's how you multiply, and you get separately real part and the imaginary part. Now, we want to divide something. Well, that's easy too. If you want to divide A plus BI divided by C plus DI, all you have to do is multiply by, how is it called, conjugate or something like this. C plus ID, ID. Oh, I'm sorry, it's minus. That's conjugate, minus. Now, what will be in the denominator? C squared plus D squared, right? I times I, it's I squared, which is minus 1, and minus. So it would be C squared plus D squared. That's the real part. Imaginary part would be CD, and minus CD, it will be 0, right? So here I will have A squared plus C squared. Now, on the top, I will have the real multiplication, which is AC plus BD, right? BD I squared and minus, right? That's the real part, and the imaginary part would be BC minus AD, something like this. Now, but this is real, so I can actually divide it separately. So it's AC plus BD divided by A squared plus C squared. So that's my real part, which is this, and imaginary part would be this. Which is this. Because now if I have two complex numbers, both are represented in a normalized form, the real part is equal to real and complex equals to complex. So I would like to finish here. I don't want to really do all this transformation, multiplication, division, etc. On the board. But what I have done, I put in the notes for this lecture on unizor.com, which is on the right from the video, all these calculations. So if anybody is really interested, and I do suggest you to go through these calculations, no matter how tedious they are. I mean, they are kind of tedious because the formulas will be big, etc. And not very exciting. But I think it's a good practice to go through these calculations and derive the formula in its final form. So that's one way of doing this thing. I might actually suggest some other ways in some other examples of doing exactly the same thing, but without using the complex numbers and the geometric sequence, etc. I think I wanted to start with this because that's what really opens up completely the whole mathematics as a field where everything is somehow interrelated. Here we have trigonometry and complex numbers and algebra of geometric series combined together, which is a rare occasion, and that's why I think it's very important to understand. The more you know, the more you see connections between different things, and that's not only the math, it's just in the world as well. You know this and you know that, and it's not really separate facts. Somehow everything is related in this world. That's philosophy. So anyway, I think it was an interesting lecture. Again, I do suggest you to go through calculations yourself and derive from this the final formula. And again, if you would like to go with my calculations on the website, on the unizor.com, and everything is in the notes for this lecture. Thanks very much. I hope it was interesting, and good luck. Hi, I'm Zor. Welcome to Unizor Education. I would like to present a couple of problems which I have already discussed in the previous lecture about trigonometric series. Problems are exactly the same. However, I would like to offer an alternative solution. And this alternative solution, I would say, is quite artificial. So it's like if you know this solution, it's kind of easy to come up with it. But if you don't know the solution, the whole idea, well, not necessarily comes as the first thing in your mind. However, knowing the answer to these problems which I have derived in the previous lecture, I can actually think about some other solution, and that's exactly what I'm going to present right now. So, the first problem was about sum of cosines, and the second problem was about sum of sines. So let's start with the cosine. So we have a problem of summation of this particular series. Okay, so we have n members in the series. The base is angle phi, and then on each step it's added delta, 2 delta, 3 delta, up to n minus 1 delta. Now, our problem is to come up with a formula which will be in a concise form reflecting the result of this summation. Now, using the correspondence between trigonometry and complex numbers, I have derived with a formula which, after certain transformations, which I also put in the notes for the previous lecture, looks like this. Cosine phi plus n minus 1 delta over 2 sine n delta over 2 divided by sine delta over 2. So that's the result. And again, knowing the result, I can come up with actually something really alternative to whatever the approach I took. I still like the approach related to complex numbers and geometrical progression better, which is in the previous lecture. However, it's interesting that it can be derived differently, and the idea about how it can be derived comes from this particular formula. Now, what does it mean? It means that the sine of delta over 2 times this should be equal to this product of these cosine and sine. And I also remember, and again, that was addressed in the previous lecture, something like if you have cosine of u minus v minus cosine of u plus v, it's equal to what? Cosine cosine plus sine sine. This is also cosine cosine and minus sine sine. So cosine will reduce itself, and what I will have left is 2 sine sine. Now, similarly, if I will add them together, I will have cosine cosine plus sine sine, cosine cosine minus sine sine. So sines will be reduced, and I will have as a result this cosine u cosine v. Now, if I want to have sine and cosine mixed together, I should really do with the sine. Sine u plus v is sine cosine plus cosine sine, right? Now, if I will add sine u minus v, what I will have? Now, this is sine cosine and plus cosine v and sine v, and this is sine cosine minus. So what I will have is 2 sine u cosine v. So basically these are transformations which I used in the previous lecture, and they are kind of trivial actually. These are trivial identities. And here is what I have. Sine. If I will multiply it by all of these, somehow sine and cosine must be played against each other. So let's see how it happens. My general member of this particular sequence is cosine of phi plus some n multiplied by delta. And I'm multiplying this by sine of delta over 2. Now, what will happen? Now, I will use something like this, right? So my n plus delta would be equal to, this is the cosine, so this is v, and delta over 2 would be u, right? So I will have, well, this is 2, so I will have to have 1/2 of this, right, here. 1/2 of sine of their sum, sine of u plus v. This plus this. So it's phi plus n delta plus delta over 2, which is sine of phi plus, how about this? 2n plus 1 over 2 delta. Is that right? N delta plus delta over 2. N delta plus delta over 2. Correct. And the cosine, no, sine, plus sine. Plus sine of u minus v. Now, what's u minus v? It's this minus this. Now, if I will change the sign and put this minus this, I will have minus, right? That's easier for me. Minus. Sine of this minus this. Now, in this case, this is phi plus 2n minus 1 over 2 delta. Correct? Now, I'm supposed to have u minus v with a plus sign. But if I will have v minus u, sine is an odd function, then this minus would be, right? And in this case, I do want v minus u, because this is kind of greater than this. So this is my formula for the common member of this series, where lowercase n is changing from 0 to uppercase n minus 1. Now, this is actually the key to the whole thing, because if you will consider this and you will really use this common member and rewrite your series, substituting for each member of this, we have multiplied by this sine of delta over 2, right? So whenever we multiply by this and then multiply by the common member, we will have this difference. And let's just do it from the very beginning. So 1/2 over. Now, this is member with n is equal to 0. And so in my parentheses, I will have sine of n is equal to 0, so it's phi plus delta over 2. This is minus sine of phi minus delta over 2. That's n equals to 0. Now, n is equal to 1 plus. Well, actually, I don't need this square bracket. This is over entire thing. Now, with n is equal to 2, I have plus sine. N is equal to 2, n is equal to 1. N is equal to 1, so it's delta plus half delta, so it's 3 delta over 2. 3 delta over 2 minus, and this for n is equal to 1 would be sine of delta over 2. 5 plus delta over 2 plus. Now, for n is equal to 2 now, sine of 5 plus. If n is equal to 2, I have 5 seconds delta minus sine of 5 plus n is equal to 2, so it's 3 seconds delta plus, etc. Now, do you see what happens here? This is what happens. This is reduced with this. This is reduced with this. And basically every member would be reduced with the one which is step over it. Now, what will be remaining is the second member from the first, which is this, and the last member for lowercase n equals to n minus 1, the bigger one. So the remaining one, if n lowercase n is equal to n minus 1, it would be sine of 5 plus 2n minus 1 over 2 delta. Close. That's what it is. This will also remain, if I'm not mistaken, right? Again, if lowercase n is equal to capital N minus 1, then this would be 2n minus 2 plus 1, which is minus 1, divided by 2 delta. And the one which has a minus would be reduced with one of the previous ones. So the only thing which remains in this case is one half the last one, which is sine of 5 plus 2n minus 1 over 2 delta, minus the second part of the first member, which is sine of 5 minus delta over 2. That's the result of the summation of the cosines. Now, so if I multiply sine of delta over 2 by all this, we get this. Now, but my formula was this. Is this the same thing as this? Let's check it out. Let's check it out. So again, if you have sine u times cosine v, remember what it is? Now, this is sine of u plus v, right? It will be sine cosine plus cosine v. Okay, then plus sine of u minus v. Am I right? Is that the right thing? And that would be 2, obviously, right? So again, sine cosine, which is this, and this is sine cosine. And then the second member would be cosine u sine v, and this is minus cosine v, which is reduced. So that's what we have. Okay. So in our case, n would be equal to nw over 2, v would be equal to 5 plus n minus 1 delta over 2, right? So let's check it out, what happens. U plus V equals to phi plus n and n minus 1, so it's 2n minus 1 over 2 delta. U minus V is equal to minus let me do it again. Phi minus n delta over 2 and minus delta over 2. That's my V. And U is equal to n delta over 2. Oh, plus, sorry. Plus. So if I will subtract from UV, I will have minus phi minus delta over 2. Okay, seems to be working fine, because this is minus phi minus delta over 2. So the sign of this would be equal to, so V minus U is equal to phi minus delta over 2. I changed the signs, right? And that's what actually this is, because I can always put, instead of plus sign, I can put minus sign V minus U, right? That's the same thing. And that's exactly what I have here. Minus sign of, and V minus U is equal to this. And this is equal to U plus V. So this, the numerator, is equal to this. And 2 will be reduced, multiplied by 1/2 would be exactly like this. So this is exactly the same formula. Now, what does it mean? It means that if I am smart enough to solve my problem, the original problem, as follows. Let's multiply the whole sum by so if this is S, let's multiply S by sine of delta over 2. If I'm smart, if I know that somehow it just occurs to me, let's multiply by sine of delta over 2. What happens? Then I will have sine and cosine, sine and cosine every member. Then I will use my formula to convert sine times cosine into a difference between two sines. And they will reduce each other, and all of a sudden I will get the final result very simply, because only the last member and the first member actually remains. Now, it's similar to summing the geometric progression. If you remember, if I have geometric progression like this, how can I sum it up without remembering the formula, of course? Well, I multiply it by V in this case. Right? Every member is multiplied by V. So this would be this would be this, etc. And then I subtract, and as soon as I subtract, I will have this. Instead of this complicated thing, I have only uv to the n, the very last one, minus the first one, which is very similar to whatever we did. We were smart enough to multiply it by something which then would be reduced and would result in reduction of all the intermediate members, only the first and the last one will be remaining. And from here I will just resolve it. And that's the formula, actually, which some people do remember, but not me. All right, so this is how you can solve this original problem if you know the results, if you kind of, well, quite frankly, if you have an experience with solving some other problems similar to this one. That's what it is. Because now, let me just replace this problem with a different one, and let's see if I will have similar results. Let's, instead of cosines, use sines. That's the second problem, which also was resolved in the course of the lecture when I was using complex numbers. What if I have this, the sines? Well, again, let's be smart, and let's multiply sum by sine of delta over 2. So, what will I have? I will use a little bit more like mathematical notation. So instead of doing this, I will have S is equal to sigma, which means sum. This is the operation of summation. The general is the general member, the common member of this series is this, where n from 0 to capital N minus 1. All right? So, if I will multiply it by sine of delta over 2, I will have sigma from n is equal to 0 to n minus 1, sine of delta over 2 times sine of phi plus n delta. That's what I will have, right? So I multiply sine of delta over 2 by an entire sum, and using the distributive law, I can always replace it with multiplication by each member, and then have a summation. So multiplication and summation are reversible in this particular case, obviously, for distributive law. All right, fine. Now, how can I deal with this one? Well, again, remember, cosine u plus v minus cosine of, well, actually, let me start with u minus v, because u minus v will result in a plus. Minus cosine of u plus v is equal to 2 sine u sine v, right? Again, this is cosine cosine plus sine sine. This is cosine cosine minus sine sine. Now cosine will be reduced, and this minus cosine and this minus would be plus, and that's why I have 2. Now, so this is what basically what I have, right? So let's consider that u is equal to phi plus n delta, sorry, and v is delta over 2. Which means that my sum would be sigma n from 0 to n minus 1. So this is u, this is v. So I will have cosine of u minus v, which is phi plus 2n minus 1 over 2 delta. Am I right? It's phi plus n delta minus delta over 2. Right, that's what it is. Minus cosine of phi plus 2n plus 1 over 2 delta. Right? So that's what we have. And now let's think about, with n is equal to 0, I will have cosine equals. Now we can convert back into the explicit sum. Phi n is equal to 0, so it's minus delta over 2 minus cosine phi plus n is equal to 0 delta over 2. Next one. When n is equal to 1, I will have cosine of phi plus delta over 2 minus cosine of phi plus 3 seconds delta. That's first two members. Now, the next one, for n is equal to 2, that would be 4, 3, 2, cosine of phi plus 3 seconds of delta minus cosine of phi plus 5 seconds of delta, plus, etc. Now, the same thing exactly happens. This is reduced with this, this with this, this with this, etc., etc. And the only thing which would be remaining is the one with the negative sign of the last pair, which is for n lowercase n equals to n minus 1. So that would be cosine of phi plus, this is my general, if n is equal to, lowercase is equal to n minus 1, it's 2n minus 2 no, this one will remain. This one will be reduced with the previous one. So this one will remain. So plus 2n minus 2 plus 1, minus 1 over 2 delta. That's the one which will not be reduced. Right. So, whenever I multiply this by this, I will have only two members, cosine of phi plus 2n minus 1 over 2 delta, with a minus sign. Right? Yes, minus sign. Because the previous one with a plus sign will be reduced. And the one which in the beginning would be with a plus sign, cosine of phi plus delta over 2. So that's the result of summation in a concise form, because now you can say that since s times sine of delta over 2 is equal to this, then s is equal to cosine of phi plus delta over 2 minus cosine of phi plus 2n minus 1 over 2 delta over sine of delta over 2. So this is the final formula, and again it can be converted into a product using the same, basically, philosophy as I was using before. Because the final formula should look like a product of two signs. Now the final formula, as I wrote it here, is sine of phi plus n minus 1 delta over 2 times sine of n delta over 2 divided by sine of delta over 2. Now the question is the product of these signs exactly the same as this? Well, again, it's probably very easy to prove using exactly the same formulas as before. So 2 sine u times sine v is equal to what? How can I get sine by sine? I have to have cosine of difference and minus cosine of sum. Now, this is the cosine times cosine minus sine times sine. Plus sine by sine. And this is also cosine, cosine, but in this case minus. So cosines will be reduced, sines will remain. This minus and this minus would be plus sign. So that's the formula. So my question is, if u is equal to 5 plus n minus 1 delta over 2, and v is equal to n delta over 2. Now, u minus v is equal to 5 minus delta over 2. Am I right? And u plus v is equal to 5 plus 2n minus 1 over 2 delta. Is that right? Okay. Oh, here, I actually made a mistake here. That should be minus. Right. So cosine of this and sine and cosine of this. Yes. Yes. I think I made a mistake when I was transferring the formulas from one to another. So basically that corresponds to the formula which I have derived in the previous lecture. And the purpose of this was, if you are experienced enough solving all these problems, different methodologies would probably come to your mind just, by themselves. So the one methodology which I was presenting on the lecture, in the previous lecture, was about using the complex numbers and geometric segments. Now, in this particular case, I actually came up with a different solution, multiplied by sine of delta over 2, and then transform product of sines or product of sine times cosine into a difference, and all consecutive members will be reduced. Well, that's another approach. You just have to, be equipped, so to speak, that you can approach it this way, you can approach it that way. There are only a finite number of approaches. So the more problems you solve, the richer your repertoire is, basically. So I will probably present some more problems in the same kind of area, and most likely either one of these two approaches would work. The only thing is, you have to recognize, you have to find out, okay, I really have to multiply by delta over 2, the sine of delta over 2. Why? Well, in this case I can actually give you a hint why. You see, the difference between all consecutive members is delta. So whenever you have delta over 2, that's half of the difference. Basically what you're doing is you're replacing two consecutive members with the middle one minus delta and middle one plus delta. Well, actually delta over 2, if this is delta. So you have the middle one, the delta is the difference, and you replace this one with middle one minus half delta, and this one with middle one plus delta. And then, whenever you're doing all other calculations, they are reducing each other. Each consecutive member would be reducing, right? Because this one is middle minus delta over 2, but in the previous step you had middle plus, so that's why. All right, so again, this is all I wanted to say about this particular problem, these particular two problems, and again, I'll try maybe to put some more on the web. And don't forget that everything will be in the notes on unizor.com for every corresponding lecture. That's it. Thank you very much, and good luck. Hi, I'm Zor. Welcome to Unizor Education. We would continue solving different problems related to trigonometric series. There is nothing really new about these problems. They are based on the same principles which the previous problems were built upon. It's just to basically to train your thought to go into this direction when dealing with these problems. One more comment which probably is necessary. There is always a question, well, why do we need this? I did answer this question many times, so let me repeat it again. I doubt very much that in your practical experience you will need to solve problems like this. They are just the brain exercises. All the different things which we can throw into the mind of a student, which would basically force him or her to creatively approach whatever problem is in front of him. That's good. That's the purpose of this website. So again, do not consider these problems as anything practical. I just can't even imagine if there are any practical problems related to this. Maybe, but I just don't know. It's only for training your mind to be creative, analytical, logical, etc. So that's the purpose, and you should really approach all these problems, most of the problems in this course, as just the training exercise for your mind. All right. Now let's do the, okay, I have two problems for today, and I will try to be accurate and not make a mistake. So the first one is sine x times sine 2x plus sine 2x times sine 3x plus etc. plus sine nx sine n plus 1x. So as we see, we have this particular series of n members, and each member is a sine of some number multiplied by x times sine of the next number multiplied by x. Now, we have to convert this series, which is very long actually, into a compact formula where obviously n and x and some trigonometric functions will be the arguments. All right, now we did use this particular technique before, and we will use it again. We will convert the product of two sines into a sum of something. Now, sum of what? Obviously trigonometric functions. Now, since I never remember any formulas except the very basic ones, I do remember that in the formula for a cosine of a sum of two angles, there are two members. One is the product of cosines, another is the product of sines. So let me just remind it. So cosine of u plus v equals cosine u cosine v minus sine u sine v. So that's product of sines. And obviously cosine of u minus v is equal to a sum of these two. So how can I get only the product of sums, of signs? Well, I have to subtract from this, I have to subtract this. Cosines will be reduced, and I will have only the product of two signs. So sine times sine minus sine times sine will be 2. Sine u sine v is equal to, from this we subtract that, right? So it's cosine u minus v minus cosine of u plus v. So that's the formula. Now, if I will use this formula for u and v equal to x and 2x, and then 2x and 3x, and then etc. nx and n plus 1x, well, let's see what happens. All right, so x is u, 2x is v, right? So I have, well, first of all, this is 2, so I have to divide by 2. So it will be 1/2. 1/2, and let's open the square bracket. Now, cosine of u minus v. U minus v. So x minus 2x, that's minus x. But the cosine is an even function, so the cosine of a negative angle is the same as cosine of the corresponding positive one. So I will just put cosine of x minus cosine of their sum, u plus v. Now, what's the u plus v? It's x plus 2x, right? So that's 3x. Good. Now, next one is, we will use 2x and 3x. 2x and 3x. Difference is, again, minus x, but cosine is even function, so I can put cosine x minus cosine 2 and 3 is 5x. So, etc. plus. And the last one would be cosine of the difference, which is, again, minus x, but the cosine is an even function, and minus cosine of 2n plus 1x. So that's what our sum has become. Now, is it better? Well, it's obviously better because these guys are the same. The number of these guys is obviously the number of members in this sum, which is n. So I can put immediately 1, 2, 1/2 n times cosine x minus 1/2 of 3x, 5x, etc. They are all odd numbers. So cosine 3x plus cosine 5x plus etc. plus cosine 2n plus 1x. Also n numbers in this sequence. Now, this is something which we have already done in the previous lecture. We were summarizing a more general series. It was cosine x plus cosine x plus g plus cosine x plus 2g, etc. Remember this? Now, in this case, instead of x, we have 3x. And instead of g, we have 2x, right? So it would be basically the same thing. So if I remember the formula for this, I can just substitute into this formula. But obviously I don't, so I will repeat the derivation for this particular formula. So let me completely omit this particular member from all further calculations, and I will just concentrate on this sum. All right? Now, what can I wipe out? I can wipe out, I guess, this one. So, we have to calculate the sum of these. Now, if you remember, again, in the previous lecture, it was quite obvious. It's very helpful in this case to multiply all the members of this trigonometric series by the sine of an angle which is half of the difference between consecutive members. So the difference is always 2x, right? 3x, 5x, 7x, etc. So the half of this distance is x. Now, why? Why am I doing it? Well, basically because of this thing. If I will be able to represent this as something minus angle, and this is something plus angle, then they will probably reduce each other. I mean, if you remember, that was actually the point. So if the difference between consecutive arguments is, in this case, 2x, I will multiply everything by sine of half of the distance, which is sine of x, and see what happens. All right. What happens is, so I do this cosine x without any changes. So I divide by sine x, and I multiply everything by sine of x. Cosine 3x sine x plus cosine 5x sine x plus cosine of 2n plus 1x sine x. Now, why did I do it? Because a product of sine by cosine I can also represent in a similar fashion. So let me just represent it first. We don't need this piece. Now, same as the difference between cosines give me the product sine by sine, the product of sine by cosine can be obtained from the difference of the sines. So let's remember the formula for sines. Sine u plus v equals to sine u cosine v plus cosine u sine v, and sine of u minus v equals sine u cosine v minus cosine u sine v. So how can I get cosine u and sine v, which we need here? I have to subtract like this. So what I will have is 2 cosine u sine v, because this will be reduced and this will be doubled, equals to sine u plus v minus sine u minus v. Right? So that's the formula which I will use. Now, u is 3x, v is x. So, and there is a 2 here, so I have to substitute 1/2 of sine of their sum, which is 4x, minus sine of their difference, which is 2x, plus. Now this sine of their sum, which is 6x, minus sine of their difference, which is 4x. Next will be 8 minus 6. You see, this is reduced with this. Next will be 8 sine of 8x minus sine of 6x, and this will be reduced, etc. So it's always the first one would be the first from the previous will be reduced to the second from the next one. So the very last one would be sine of their sum, which is 2n plus 2 of x minus sine of their difference, which is 2n x, which is also will be reduced. So what's left is this and this. So it's n over 2 cosine x minus 1 over 2 sine x. Then another 2, so I will have to put 4 here. And the only thing in the parentheses, in square brackets, would be sine of 2n plus 2 minus sine 2x. Now, this is basically the end of it. I mean, if you want, you can convert the difference between signs into a product, so the formula might actually look a little better, or not better, I don't know, it just doesn't really matter. But in any case, this is one of the final formulas which can actually be stopped at, and no further reduction is necessary, because you don't need all these dot things, which signify there are certain numbers, certain terms, members of the sequence which we didn't really write. This is a compact formula which represents this particular series, which we can a little bit change as well, but doesn't really matter anymore. We have the compact formula without any kind of unnecessary dots. All right, that's basically it for this particular problem. Now, as you see, I did use a couple of formulas here, but it's not really something which I remember. I derived it right on the fly, and the only thing which I do remember, and quite frankly I do remember it quite well, it's sine of the sum and sine of the difference between two angles, and cosine of the sum and cosine of the difference. This actually is something which you probably have to remember, and it's not really a big deal. Only like 2 formulas. You don't really need the second one, because the second one can be derived from the first one. Like for instance, if instead of v you put minus v, cosine of minus v would be the same as cosine of v, but the sine of minus v would be minus sine of v, right? So this second formula is derived from the first one, because sine is an odd function and cosine is an even function. Same thing here. If you know the sum, the cosine for the sum, and that's the minus sign here, you have to really remember that for a sine, this plus corresponds to this plus. For a cosine, this plus corresponds to minus. But how to derive it for minus v? Well, if you substitute minus v, the cosine part remains the same, because the cosine is even function, and the sine would reverse, and that's why you have, instead of minus, you have plus. So only 2 formulas basically: sine of sum of 2 angles and cosine of sum of 2 angles. Everything else is derivable, and derivable quite easily. As you see, I did it right on the fly basically. All right, that's it with this particular problem. Let's wipe it out and go to the next one. Okay, second and the last problem for this lecture is the following. Sine cube x plus sine cube x plus d plus sine cube x plus 2d, etc., plus sine cube n minus 1 x, sorry, sine cube x plus n minus 1 d. So from x plus 0 d to x plus n minus 1 g, n members. And we have to calculate this sum. Well, here is something which you might remember or might not. in one of the lectures, I think one of the first lectures about trigonometric identities, I derived the formula for sine of triple angle. And that formula actually contained sine in the third degree, sine cube. So I would like to use this formula to express sine cube as a sine of a triple angle and something else. But I do need the formula for sine of the triple angle, which again I don't remember, but we can very easily derive it, right? So sine of 3 phi equals, well, that's obviously sine of phi plus 2 phi equals sine phi cosine 2 phi plus cosine phi sine 2 phi equals. Now cosine 2 phi, or cosine of phi plus phi, is cosine cosine minus sine sine. But angle is the same, phi plus phi, so it's cosine square and sine square. So sine phi cosine square phi minus sine square phi plus cosine phi. Now sine of 2 phi is sine cosine plus cosine sine. But again, since angles are the same, phi and phi, I can just put 2 sine phi cosine phi equals. I would like everything to be in sines, which means this cosine I will replace with 1 minus sine square phi, if you don't mind. And here you see cosine and cosine would be cosine square. I also replace it with 1 minus sine square phi. So what will I have is sine phi times 1 minus 2 sine square phi plus 2 sine phi times cosine square, which is 1 minus sine square, equals. Alright, now let's open all these brackets. Sine phi minus 2 sine cube. Sine phi minus 2 sine cube phi plus 2 sine phi minus 2 sine cube phi equals. Sine and 2 sine, that's 3 sine phi minus 4 minus 2 sine cube phi. Now, why is it important? Well, because I can express sine cube in terms of sine phi and sine 3 phi, right? So sine cube phi is equal to 1/4, right, of 3 sine phi minus sine 3 phi. All right? If sine of 3 phi is equal to this, then 4 sine cube is equal to 3 sine minus sine of 3 phi, and then divide by 4. Right. So, what it means is that every member I can replace with 2 members and basically completely separate this particular sequence into 2 different sequences. One with single angles and another with triple angles, right? So, this sum is equal to, I don't really need anything here. That is already done. So that's my formula for sine cube. So equals to 1/4. Now 3 sine x minus sine of 3x. Right? Actually, I don't need to close this. Let's just continue. Plus 3 sine of x plus d minus sine of 3x plus 3d, etc. And the last one would be 3 sine of n minus 1 x minus sine of 3 n minus 1 x. Now, as you see, I can separate these guys from these guys and have basically two different things. One is 3/4, this is 3 and this is 4, right? Of sine x plus sine x plus d plus sine x plus 2d plus etc. plus sine of n minus 1, x plus n minus 1d. Oh yeah, I have made a mistake here. It's d, and this is plus x. And same here. This is d, and this is x, right? Yeah, that's better. So, one is these guys plus, another is, well, actually minus, not plus, minus 1/4. This is 1/4. And I have here sine of 3x plus sine of 3x plus 3g plus sine of 3x plus 6d plus sine of 3x plus 3n minus 1. So we have two sums. Each one of them is actually the same as the one which we considered during one of the first lectures dedicated to series. And again, you can use exactly the same approach as in the previous problem. The difference between these two is d. So you have to multiply everything by sine or cosine of d over 2, and each product can be represented as a difference between two different angles, and everything would be basically reducible, except the first and the last one. And similarly with this case, instead of x, you have 3x here, and the difference is 3g, not d, which means you have to multiply it by sine or a cosine of 3g over 2, right? And again, the whole thing will be reduced as soon as you convert the product of trigonometric functions into the sum or difference, actually. So I don't want to do these calculations because it's obvious now. We are reducing the problem which we don't know how to solve to two problems which we do know. We already did this particular thing a couple of times, so that's why I don't want to waste time. But I do refer you to either corresponding lecture or basically the notes on unizor.com to this lecture, which do contain basically the whole sequence of formulas, etc. I do recommend, however, you do it yourself first, and then look at the result, check it with the answer which is on the side, etc. Well, that's it for today. I do recommend you to use full functionality of unizor.com to basically convert your studying into a real educational process. And to this you need some supervisory responsibilities, either You yourself can be your own supervisor under a different username signed into the system, or your parent or your teacher or somebody else. They will enroll you as a student into the course, and then you can take exams, and you will see the score on these exams, etc. Well, that's it for today, and good luck to you. Don't forget, try to do everything yourself, and only then check the answers. Thanks very much.